So we're going to cover soil fertility. We're going to do a section of it before lunch and then a section after lunch. So we're going to talk about plant nutrition and functional soil model and soil chemical properties as they relate to soil fertility, because I think Melissa will agree with me that soil fertility is really an applied area of soil chemistry. So there is a fair amount of soil chemistry in it. If that wasn't one of your favorite topics, what can I say? It happens to be, as far as I'm concerned, the view of the soil that explains, for me, most of what's going on. And I would like to know who here in this room has had a basic soils class at some point in their life. I don't care how long ago. Fair number of you. Crops? Botany? Okay, so a lot of varied background here. Okay, so plant nutrition. What topics might you want to know about as you prepare? I think we need to talk about the growth factors. We need to have a good understanding of the plant nutrients and how they're categorized. We need to know how nutrients get from where they are to the plant. Those are the mechanisms of delivery. And we need to be aware of the law of the minimum, because it has a lot of impact on practical plant growth. The growth factors, of course, are something you learned about in soils and in crops and maybe even in botany. There are 6. Nutrients are just one of them. Plants need water. Plants need oxygen, especially in their roots. Sometimes that's a limiting factor. They need a certain temperature depending upon where they evolved and what kind of an environment they live in. Some things can withstand quite a bit of cold, other things can't. You can grow spinach in March, but you can't grow tomatoes in March around here, right? Spinach doesn't mind the cold weather, tomatoes will freeze, all right? They need carbon dioxide for photosynthesis. They need mechanical support. That's one of the big things soil does. It supports those roots. And then they need nutrients. And I think it's always helpful to keep all of these in mind, especially if we're in positions like some of you work for companies or you give advice to farmers and things may not be growing well. Don't always focus on nutrients. Think about all of these, because it could be compaction that's leading to inadequate oxygen in the root zone that has nothing to do with your nutrient supply. So just keep an open mind about this. A lot of times when farmers think there's a problem, the first thing they think of is nutrients, and it may or may not actually be the issue. So what is a nutrient? Well, this definition was agreed upon by plant physiologists back in the 50s. It's an element that has a direct effect on plant growth and metabolism. It's required to complete the vegetative and the reproductive stages of life, and it can't be replaced by anything else. It must itself be required. And I'm not into human nutrition definitions, but I suspect it's probably similar in animal and human nutrition also. So what are the nutrients? And you're probably aware that there is a kind of a textbook that goes along with this class. It's called the Mid-Atlantic Nutrient Management Handbook, and several times I'll refer to it. This is table 4.2 in that book. So first of all, there's what we call the non-mineral nutrients. Non-mineral means they don't get it from soil, right? As opposed to the mineral nutrients that plants do get from soil. So if you pick up a book on plant nutrition, it'll have both. If you pick up a book on mineral nutrition, it'll only talk about the stuff you get from soil. So the mineral nutrients are typically broken down into 2 groups, and this is dependent upon how much we typically find in a plant. Right? Macronutrients are the ones we find in larger amounts, and they too are broken down. Primary, nitrogen, phosphorus, potassium. Secondary, calcium, magnesium, and sulfur. And then a whole list of micronutrients. Now again, depending upon what book you pick up, there may be other things in this list, because there's not universal agreement, or maybe people don't keep up with the literature, one or the other, in terms of what is actually a micronutrient for plants. But this is the list that's included in the Mid-Atlantic Nutrient Management Handbook. Typically, macronutrients exist in plants on a dry weight basis in percents, and micronutrients are measured in plants in parts per million. Right? And it might be a lot of parts per million, like iron might be as high as 100 parts per million, and molybdenum might only be a fraction of a part per million. So in terms of understanding how things behave in soil, it's important to know how they exist in the soil in terms of their ionic state. All right? Now there's a TV channel, I'll call it, on television called Ion. Anybody watch it? They play Law and Order repeats, so I watch them, right? Because I'm a Law and Order freak. But anyway, they say ion, positive television, or something like that, and I'm going, oh, wait a minute. Ions aren't always positive, you know? At which point I should go, Trish, you're home now. Stop it, all right? Anyway, ions can be positively charged That is, they're cations, and that's how that's pronounced, cation. I know it looks like it should be cation, but it isn't. Anion, negatively charged ions, and neutral. And it turns out that some of the nutrients exist as a cation. They are cationic in form. Some of them are anionic. Some have both, and some are neutral. And in terms of understanding how they behave in soil, that's important, because soils in the temperate region tend to have a net negative charge. Right? So if you're positive, you're going to be attracted to your soil. If you're negative, you may not be so attracted to the soil unless there are other things going on. Okay, so again, this is back to the Mid-Atlantic Nutrient Management Handbook. This is Table 4.1. And on the left side here, we have all the nutrient forms that exist as a cation. And on the right, we have all the nutrient forms that exist as an anion. And like I said, some of them are both. Nitrogen has a cationic form, ammonium, but it also has an anionic form, nitrate. And that's important because ammonium, as a cation, would be attracted to soil clays. We'll talk a lot about them later, more than you probably want to know. And anion, nitrate is a small anion, and it is not attracted to anything in soil to any great extent. It tends to spend its time in the soil solution, and it thus can move down with the soil solution as precipitation occurs. So cations have the potential of being absorbed onto soil particles because they are, in fact, oppositely charged from the soil clays. Right? Boron is a good example of a nutrient that can exist in a variety of forms. It can exist as undissociated boric acid that has no charge, it's uncharged, or it can exist as two different borate anions. Okay? And it turns out that phosphate and sulfate and borate and molybdate have some similarity in terms of how they behave. Some differences too because they're not the same size, but if a soil has a high propensity to absorb phosphate, it might have a high propensity to absorb some molybdate also. So again, we can make some general assumptions about how something might behave based on its charge. Okay, so there are some terms you're probably going to want to know because they're the subject of questions. You are, after all, getting ready for a 100-point multiple choice question. So I would know what mineral nutrients are. I would be able to identify them. Non-mineral nutrients, macronutrients, primary nutrients, secondary nutrients, micronutrients. Kind of have that organizational chart so that you can respond to questions on that. And we'll have a practice in a little while. So the whole, sometimes we run into the issue of, well, what happens if a nutrient isn't there in adequate supply? Okay, what happens to the plant? And can I have too much? That's often a question. So there's a diagram here that I think might help us with that. This is from a book on plant analysis that I love. It has lots of great information in it. And this is the relative concentration of an essential element in a plant, all right, from very low, low, intermediate, high, and very high. And this is the relative plant growth up to 100%. So at 100%, the growth of that plant is not being limited. Well, if there's a very low supply of an essential element, the growth will be severely limited. All right? As you move up into low, the growth increases as the concentration of the nutrient increases. And you get to a point where, based on that nutrient alone, everything else being okay, that you'll get optimal growth and things will level off. And in some cases, particularly with micronutrients, it is possible to have too much of a material. And in that case, you can actually get a yield decline due to an excessive amount of that. Now, let me emphasize that the only times that has been demonstrated are with micronutrients, never with the macros. All right? I use this case because it was one that kind of hit home, particularly since of the similarity in the crops. But in the 70s, I lived out in the Rio Grande Valley in southern New Mexico, and pinto beans are a staple in Mexican-American cuisine. And typically when farmers took their land out of alfalfa, they grew a lot of irrigated alfalfa for some feedlot dairies down near the Mexican-U.S. border, they rotated into something else for a year to make a quick cash crop before they went back into alfalfa. And what they would want to grow would be pinto beans, because there's a huge market for pinto beans. Well, the thing is, there's on those soils, alfalfa needs supplemental boron. So the potassium fertilizer that farmers bought to put on after each cutting of alfalfa was spiked with some boron to meet the nutritional needs of the alfalfa. Okay? But it turned out that there was enough boron left in the soil after that that the pinto beans experienced boron toxicity on many of the soils. Now, that just blew my mind because beans and alfalfa are in the same family. They're all leguminaceae, and you think, well, you know, they should have similar needs. But this wasn't the case. So what's perfectly okay for one crop may be too much for another, and as I learned then, even if the crop is in the same family. So how can you tell if nutrients are deficient? Well, there are all kinds of things out there that have pictures of what nutrient deficiencies look like in different crops. And there is some difference across crops. There's some commonality, but there's some difference. This is just one little brochure that comes from the Ontario Ministry of Ag and Forestry. And it's a nice little one page. And you can see that you know, some of them have burning, some of them have color changes. Phosphorus is kind of typically the red. So where does the, well, first of all, what's occurring? Is there discoloration? Is there dying? Where is it occurring? Between the veins, old tissue, young tissue? There's dichotomous keys that help you figure this out if you're out in a situation where you're observing some of this. Let me tell you, though, that if you're actually seeing a nutrient deficiency, you've got a pretty bad problem. Because for a whole period, for a whole range of nutrient concentrations, nothing's obvious. You're just getting a yield reduction. So we'll have a copy of a bulletin tomorrow that talks about plant tissue analysis. And that's one thing, one tool people can use over and above soil testing to kind of diagnose whether or not you might have some nutritional problems in your crops. And by the way, a lot of vegetable producers do some routine tissue analysis as a follow-up to soil test to make sure that the crop is actually getting enough of the nutrient. And I want to talk a little bit again about this hidden hunger thing. This is when you're not getting the yield you could, you're not getting optimal yield, but there's no visual symptom. And this is a term that used to be called hidden hunger. It's kind of dropped out of use in agronomy now, and it's used more for human nutrition. It's now, if you do a search in Google for hidden hunger, you'll get all these things about how many people worldwide need micronutrients, and you can't even find anything about plants anymore. But there's a range in here where you don't see anything, but your yield reduction is pretty severe. Now, a lot of people seem to think, the plant physiologists seem to think that by the time you see something, you're down at the 50 to 60% yield potential, right? And if you're a vegetable producer with a high value crop, you sure don't want to be there. Okay. Well, what happens when more than one nutrient is inadequate? Right? Well, we've got some work that came out of the 1800s by a German scientist, ag scientist Liebig, and a colleague, well, he wasn't really a colleague, they weren't even friends, Sprengel. Liebig's law of the minimum, I now call it legal Sprengel law of the minimum because Liebig essentially stole Sprengel's work and wrote it up, and because he was a big name, he got all the credit for it. Happens a lot in science. What it says is that growth is limited by the growth factor present in the least adequate amount. Right? And yield is proportional to that most limiting factor. And even Liebig had demonstrated this in this example. That's why it's in German, because Liebig was German. So the barrel works out perfectly. You may have adequate amounts of a whole bunch of other things, but if you have inadequate, in this case, nitrogen, your growth is going to be limited by the amount of nitrogen that's in your system. And if you bump your nitrogen up to optimum and you still have inadequate phosphorus, then your phosphorus is going to limit things. So growth is limited by the factor that's present in the least adequate amount, and growth is proportional to that. All right, so examples of micronutrients are the following, okay? Think back to what we talked about a minute or two ago, and let's get our timer going. Okay, so macronutrients, excuse me. Can it be A, nitrogen, iron, potassium? No, because iron's not a macro. Can it be B, phosphorus, nitrogen, calcium? Yeah, and in fact, B is the correct answer. Can't be C because zinc is a micro, not a macro. And it can't be B because cobalt is a micro, not a macro. Okay? So don't miss one of these. These are the easy ones. Okay. Now, you looked at a pie chart a little while ago, and I like that for a first cut model, but we're going to go beyond the pie chart in a minute, and we're going to expand our vocabulary and concepts a little bit, and then we're going to look at a two-dimensional slice of soil to try to get a sense of how these different components we talk about actually exist in space. All right? So anyway, this is the soil model I've been using for a number of years, and I want you to tell me what some of these are. First of all, there's something over here on the left. It's 3 compartments, E, F, and G, and they kind of border on one another, and that's signifying that sometimes it's hard to tell which one you are. Whereas over on this side, we have C and D, and they are 2 different camps. You're one or the other, and it's really clear. And in the middle, you have A and B, and this little accordion thing means that A and B go back and forth. Another clue is the plant's growing in it and getting stuff from it directly, okay? Okay, well, let's look at this, all right? Over here on this side, these are your inorganics, your minerals. You have primary minerals and secondary minerals. Now, we all took geology at some point in time, might have been 6th grade, but you took it, all right? And we learned that primary minerals are minerals that haven't changed their chemical form since the solidification of magma, all right? Whereas secondary minerals form from the breakdown products of primary or other secondary minerals. Well, in the soils, we have both. If you look at a soil and you can see quartz crystals, that's a primary mineral. That hasn't changed chemically since the magma with which it existed was solidified from magma. We have a lot of, up in the Piedmont where I live, we have a lot of muscovite in our soils. That's a primary mineral, all right? Whereas secondary minerals tend to be what we call our clay minerals. They can be oxides, they can be silicates, but they're tiny, and they've probably formed in soil or other environments and where they were formed and were transported to where they are now. But there's a massive difference between these. These are old, they haven't changed since they were first solidified from magma. These changed from something else, all right? As a general rule, our clay size fractions, the tiny particles, tend to be primarily secondary minerals, although they may have very tiny particles of primaries. Our primary minerals make up our sand and a lot of our silt-sized particles. Right? Now over here on this side, we have organic solids. We have our biomass, the stuff that's still alive now, the humus, the stuff that's been worked over and is highly resistant to any further decomposition. Not that it doesn't decompose at all, we can't say that, but it's highly resistant to further decomposition. And then in the middle, we have these residues and byproducts. Residues are the things that fuel our biomass. Byproducts are the things our biomass makes, all right? If we don't have this, we don't have a good soil. And the emphasis on soil health is to keep a healthier, more vibrant, larger biomass by having more residue, gotta feed them, and they will make byproducts that make good structure, right? The reason we have soils that aren't so healthy as we define it now is because we haven't fed them enough, all right? We haven't left enough residue. We haven't fed our biomass, so they haven't been able to do their job of producing the byproducts that make that good, stable structure. And in the middle where our plant roots grow, we have either soil solution, soil water, or soil air. And yes, this goes back and forth. If we have a very heavy rain, this entire thing could fill up briefly with soil solution, but then gravity will drain some, and the water will go down, and the air will come back, okay? All right, well, this is a two-dimensional slice. This occurred in a book a number of years ago. I loved it because it was the first nice two-dimensional picture anybody ever did, and I had one of my students color it one summer with colored pencils. So you can see we've got these huge sand and silt particles here. We've got some clays and little packs in a couple places. This must be a loamy sand or something because there's not much clay here. We have pores that have water, and if there's water in them, there's critters living in them. Then we have these big pores here where there's air, and that's good because the roots need air, and we've got a lot of terrestrial creatures that live there too that would drown if it was submerged very long. So this is a two-dimensional slice, and you can see how the living stuff, the roots and the fungi that grows around them, and the critters and the bacteria and the clays actually come together and make a three-dimensional environment that has a wide variety of niches. So you have all kinds of creatures that can live there. So let's talk a little about the chemistry of things. The fact is that water and nutrients are held on surfaces, all right? Surfaces is a key to reactivity, all right? And if you look at this graph here, you can see that sand has very little surface area, the silt particles have more, clay has more, and what they call colloidal clay, or the very tiniest of clays, has the most. So this would be square meters per gram, something like that, some measure of area per unit mass. And whether you're talking about surface area per se or swelling potential, ooh, that could be a problem with some clays in some parts of the country. Not much of a problem here. We don't have those clays. Absorption of water or nutrients, water holding capacity, and also plasticity and adhesion. They're all related to surface area. And so the more clay we have in the soil, the more surface area we have, the more absorption of water and nutrients that can occur. Now, that's not to say that you want 100% clay, because you sure don't, all right? There's physical reasons why that is a nightmare. But you certainly are helped by the component of clay you have in your soil because of its ability to hold water and hold nutrients. And this is another picture. This showed up in 2011. It was the 75th year of the Soil Science Society of America, existing discreetly from the Agronomy Society, and they put out this special issue, was the history of everything. And one of the authors made a diagram somewhat like this. We basically redrew it. But you can see clays. These are your clays. They tend to be clayey, all right? And you've got humus. You've got humus here. That's the brown. And this gold stuff is your iron oxides, right? And your stars are the crystalline iron oxides. So you've got amorphous stuff and you've got crystalline stuff. So this is what's going on with our very fine mineral material and also with our humus. This stuff is interrelated with one another. It doesn't necessarily exist discretely. Even the crystalline iron oxides have some of the new amorphous stuff kind of slobbered over the surface. And you can see here where the humus is kind of bonding three little clay platelets together. Right? That's essentially protecting the surfaces underneath it and keeping them from reacting. And over here you've got the trifecta. You've got iron oxides kind of mushing together the clay particles and then humus mushing over that. So this is how it really is in that clay fraction. It's very complicated. And all three of your really important materials, your layer silicates, which I'll talk more about, your iron oxides, and your humus all kind of intermix and slop around, okay? Especially the amorphous oxides and the humus. They're amorphous in shape, and they can coat things and hold things together. Okay, so let's move on a little bit to soil chemistry and soil fertility. We need to talk about pH because it affects many other things in addition to being very important itself. We're going to talk about soil clays and their surfaces. All clays are not equal, and we're going to end up by talking about how we manage soil pH. First of all, can anybody tell me what pH stands for? What's the P and what's the H? Chemistry 101 coming back to you? No? Okay. Well, P means negative log. It's a math term, all right? And H stands for hydrogen ion concentration, or if you've had physical chemistry, hydrogen ion activity. And if you've had physical chemistry, you can do this course for me next year, okay? You probably had physical chemistry, Gary, haven't you?
Yes.
Yes. Well, we kind of slop around here and use concentration when in fact we mean activity, okay? You okay with that? All right, so pH, negative log. Using P next to a number is simply a way of making it easier to talk about small numbers, in my opinion, all right? Hydrogen ion is referring to the concentration or the activity. At low levels, there's not too much of a difference anyway, at least from my point as a soil scientist. So pH is the negative log of the hydrogen ion concentration, all right? Now, you know from high school, that if you see x equals minus y, they're inversely related, right? As one goes up, the other goes down. And that's exactly what happens here, all right? So they're inversely related. As the pH increases, the hydrogen ion decreases. And we have descriptors. If it's pH less than 7, we call it acidic. If it's greater than 7, we call it basic or alkaline. And if it's right at 7, it's called neutral. And that's pretty true across disciplines. But here's a relationship chart that shows you the hydrogen ion concentration in moles per liter, expressed as a decimal fraction, expressed in scientific notation, and expressed as a negative log. All right? So you can see that it would be a little uncomfortable to walk around talking about a soil that had a pH of 7 by saying, geez, what is this? Tens, hundreds, thousands, 10,000s, yay. You know, you see why they did this? Okay, because these are clumsy. Now you could say my hydrogen ion concentration is 10 to the minus 6.2, okay, but you could also say my pH is 6.2, all right? So let's look at this. For example, 1 year on the exam, folks were given a hydrogen ion concentration expressed as a decimal form and expected to be able to convert it to the pH. And I want you guys to be able to do that. So here's the trick. Remember Melissa talked about gimmicks? The gimmick is, how many places do you have to move the number to the right to get a whole number? Okay? 1, 2. 10 to the minus 2. Negative log of 10 to the minus 2 is 2. Okay? Down here. 1, 2, 3, 4, 5, 6. 10 to the minus 6. pH is 6. Okay? So don't miss that 1 point. That's an easy one. So pH affects lots of things in our environment. Here's some stuff in our everyday life: battery acid, stomach, vinegar, coffee, seawater, bleach, sodium hydroxide. Extremes on any end are bad. You know? Pure hydrogen peroxide is just as destructive to your tissue as pure hydrochloric acid. And over here on the left side is what we see in some soils. Typically around here, our forest soils tend to be from, I've seen as low as 3.9 up to about 4.5 in their native state. Our land here was quite acidic. And we need to lime soils in Maryland in order to bring them up into a range where it's optimal for the crops we want to grow, unless you're growing some acid-loving plants. Okay? In some parts of the country where there's less precipitation, our soils are actually alkaline. They're actually calcareous. The land that my husband and I owned in the Rio Grande Valley had a 8% calcium carbonate in the clay fraction. Okay, it was a calcareous soil, and it had a pH of about 8.6. Also out west, we get what's called sodic soils. That's a very bad condition for your soil to be in, and they can have a pH up in the 9s. We do have some of these acid sulfate soils in Maryland. It's a pretty interesting phenomenon. There was just an international conference on this, I believe it was last summer. These are soils where there's materials in the soil that oxidizes and makes the pH down around 2. Nothing grows in these soils, so they're quite problematic. Okay, if the hydrogen concentration of a soil is 0.00000001, its pH is. Very good. The answer is 7. 1, 2, 3, 4, 5, 6, 7. I had to move the decimal 7 places to get a whole number. Okay, so we're going to talk a lot about charge, cation exchange capacity, why we have it. The knowledge areas don't say much about why you have it, but I don't like to be told something without understanding why it's happening, so you're going to have to put up with my propensity to answer this question as we work through some of this. CEC, an important, just seminally important property of the soil, cation exchange capacity. It's essentially the ability of your soil to hold cations on charged sites. So it's also a measure of the net negative charge of a soil, because it's not going to hold charged things unless it's negatively charged. And for years it was expressed as something called milliequivalents per 100 grams. It's now expressed in centimoles per kilogram. So depending upon what book you have, the units may change, but the numbers don't change. Fortunately, the new units are about the same. So why is it important? Well, the exchange phase is the storehouse of cationic nutrients. Right? It's where they're kept in reserve for future needs. They are protected from leaching when they're on the exchange sites. But please understand that there's dynamic equilibrium between what's on exchange sites and what's in the soil solution. So while they're on exchange sites, they're preserved from leaching, but they can move out into the soil solution where they no longer have that protection. So here's an example. This is a clay mineral, and we'll talk about why I drew it that way in a minute, but it's got charges and 3 different layers. Remember I said they're like plates, all right? And right now, that clay mineral, the charge on that clay mineral is neutralized by the exchangeable cations that are all around it. And it turns out there's 13 calciums, 4 magnesiums, 2 potassiums, and 6 hydrogens. So you got a soil test that said you don't have enough potassium in that soil, so you added some muriate of potash, right? Well, what did that do? Well, it dissolved into the soil solution, and you just bumped up. Now, this just looks at changes in the soil solution. You've just increased the potassium by 9 units and the chloride by 9 units. In doing that, you upset the balance that existed at that point in time. So there's going to be a new equilibrium established, right? So what happens? Well, some of the potassium exchanges with other things on the clay minerals. Not all. And after the equilibrium is reestablished, you still have 2 more potassiums out in the soil solution than you had before. But let's look at what happened. You used to have 13 calciums, now you only have 11. You used to have 4 magnesiums, now you only have 3. Okay? You do have more potassiums on your reserve, and you also got one of the hydrogens kicked off. So by fertilizing with potassium that you needed, your soil test indicated you needed, you're increasing what's in your soil solution, and you're increasing your reserve. But the point I want to make is you do that at the expense of other things, all right? Some of the calcium and the magnesium, which plants need too, is now out in the soil solution where it's no longer in a protected place, all right? There's always consequences to things. You might do something because you think it's good, but there's always consequences. And we know this from having lived our life, right? All of you are over 18 in here. You know about consequences. Nothing happens without consequences. Same thing here. Okay. So, why is there charge? Why did I show all those negative charges in that clay? Well, first of all, there's 2 kinds of charge. There's something called isomorphic substitution, which leads to something that we call permanent charge. And this is where most of their clay minerals get the charge. Isomorphic substitution. All right? This is a substitution of one ion for another while the mineral was forming. It's not anything that's happening now. All right? Then there's another mechanism for charge, protonation and deprotonation. Protons are nothing more than hydrogen ions. So this means you're gaining or losing hydrogen ions at surfaces, all right? And it's the main mechanism for hydrous oxides and organic matter to get their charge. It also occurs on the edges of clay minerals, okay? So we're going to talk a little bit about this, more about this and some about this. Okay, well these are the building blocks of what we call aluminosilicate clays, layer silicates, clay minerals, okay? They have 2 different kinds of structural units. They have the silica tetrahedron and they have aluminum or magnesia octahedral. And they can be bonded together, all right? So you can get a 2-to-1 and a 1-to-1. And I'm going to show you a 2-to-1 here. I'm going to show you how we get the charge. Because I had to know how this happened. And I was reading about soil clays and going crazy and not understanding the little diagrams of styrofoam balls. And when I saw this, I went, I got it. Finally understand it. You know, it was one of those aha experiences. Now, first of all, I want to talk about unit cells. The unit cell is the smallest repeating unit in a mineral, all right? So, you know what table salt is? What's the chemical formula of table salt? Sodium chloride, okay? When you pick up a grain of sodium chloride, is it just 1 sodium and 1 chloride? No, it's a whole bunch of them, right? But we communicate by the unit cell, right? So this is a unit cell over here. And this one over here is an uncharged unit cell of a 2-to-1 mineral. It's got a layer of silica here, it's got a silica layer here, and it's got an alumina layer sandwiched in between. And they're bonded together by the mutual sharing of these oxygens. So they're actually bonded, all right? So in this unit cell, there are 6 oxygens on the outside, 4 silicons in the middle, 2 oxygens and 2 hydroxyls, 4 aluminums, then 4 more oxygens, 2 more hydroxyls, more silicas. So this is just a mirror image of this, all right? This silica is bonded together by this alumina by mutually sharing this oxygen. This silica layer is bonded with this one by sharing these, okay? Now, right now, if you look at these charges, 12, 16, 10, 12, 10, 16, 12. You've got 44 pluses and 44 minuses, so there's no net charge on that unit cell. So what can happen while these clays are forming? Remember, they're secondary minerals, all right? Well, it turns out that if the environment has a fair amount of aluminum in it, instead of getting 4 aluminums in this layer, you can get 3 silicons and 1 aluminum, all right? Now, I want to tell you that there can also be substitution here, and in this case, there is substitution here. 1 aluminum for 1 of the 4 silicons. Isomorphic substitution. They substitute. First of all, they're there. They're a similar size, so they fit in the chemical structure without disrupting it. Not everything can fit, right? But because they can substitute, you ultimately can get charge in that unit cell. So now, still 12, 15 instead of 16, still 10, still 12, still 10, 15 instead of 16. So now we have 42 positive charges and 44 negative charges, or this unit cell has -2 negative charge on it. Just that one unit cell. That's how this happens. Now, you probably know that there are entire books on things called clay mineralogy, and you probably know that I have all 2 editions. Okay? Now, there are probably hundreds of clay minerals. It depends upon who substitutes for what, who found it, and they give it their name. It's how you immortalize yourself in science. Get a clay mineral named after you, get a procedure named after you, right? Okay, so, and some of the differences are insignificant from our point of view, okay? But the thing is, substitution can happen while the mineral is forming. So until it weathers into something else, it's going to have that charge. Now, the fact is that a clay mineral we might look at, and this is pretty small. Who has a book here? Can I have your folder for that? Thanks. So let's say this is a clay mineral, okay? We look at it under an electron microscope. It's probably 10,000 unit cells, maybe 100,000 unit cells. Some of those unit cells have charge and some of them don't, okay? But to the extent that they have negative charge, oppositely charged ions, cations, are going to absorb to it to neutralize that charge. So we usually think of clay minerals as being covered with a swarm, and that's the term you'll see written, a swarm of exchangeable cations. Okay, so we have some major players here. I'm not going to bore you with all 100 plus of names that are out there, but this kind of distills it down to the major family. We have kaolinite. We have a lot of that in our soils. It's a 1-to-1 clay mineral. It has 1 alumina layer and 1 tetrahedral, or 1 alumina layer and 1 tetrahedral layer. It's considered a 1-to-1, and it doesn't have a whole lot of charge compared to some of the others. Its cation exchange capacity usually is between 3 and 15 milliequivalents per 100 grams. Then there's something called montmorillonite. It's a 2-to-1. It's got 2 tetrahedra with an alumina sandwiched in between, and it's not strongly bonded to itself, so there can be exchangeable cations in between. It's a 2-to-1, and it has a lot of charge. All right. Then there's hydroxide or mica. They're 2-to-1 also, but they have strongly bonded potassium between them, so they don't come apart. 2-to-1, but less charge, because only the external area is available for exchange. Then we have vermiculite. We have some of this in some special regions of Maryland. That's a 2-to-1. It has magnesium in between. A lot of charge. Chlorite. We have some of this in our soils. This is interesting. It's a 2-to-1 with another layer in between, another alumina layer in between. It's called a 2-to-1-to-1, and it's 15 to 40. All right. So you can see here that someone might say, "Oh, well, my soil has 20% clay in it." Well, that's a nice thing to know, but it's not all you need to know, because if it's 20% this, you might have some trouble if you want to build a house on it or a road. All right. Whereas if it's 20% this, no shrink swell problem, also not as much nutrient holding capacity. All right. Some of these, this one is a very, very high shrink swell clay. It poses huge problems for establishment of bridges and buildings in the regions where it exists in the soil surface. Typically has to be removed in order to build on it. It's not uncommon for it to shrink to 10 times its volume when it's wet and then shrink back when it's dry. So you can imagine trying to build a house with bridge on it. Very, very high shrink swell. We don't have We don't have soils with high amounts of that in Maryland. This is an old graph. This is from 1968. As far as I know, no one's updated it. When I asked Dr. Ravenhorst for anything, this is what he refers me to. But this shows a map of Maryland and the different clay minerals: montmorillonite, chlorite, vermiculite, mica, kaolinite, glauconite, and shows where they exist either as very little, 0 to 10, 10 to 30, 30 to 70. And you can see that we're kind of a mixed bag, you know. There are places where we have a mixture of many, many different things. We may not have any of this or this, but we have a mixture of chlorite, mica, vermiculite. So the clay mineral map is kind of varied. Unlike some other states where I've lived, I spent 4 years in Georgia working on my doctorate, and there kaolinite was it. If you looked at the map of the clay minerals of Georgia, everything was kaolinite, and there would be none of these others. Here we're more mixed mineralogy. And if you look at that map and you look at this, you see there's a lot of overlay, right? The same patterns that we saw in the physiographic provinces shows up in the clay minerals, and that's because the clay mineral you have in your soil is primarily a function of two things. What was your parent material? What was your beginning stuff? And how old is it? How long has it been out in the environment where it's weathered? All right? So the clay minerals we have are highly dependent upon the parent material they started from. That shouldn't surprise anybody. I always like to say, with my parentage, there's no way I could be 6'2" and blonde, right? No way. Parent material doesn't allow it. Same thing with rocks and clays. You start out with a certain kind of rock, there's a certain suite of clay minerals you're going to end up with, not another. Right? So what about variable or pH-dependent charge? Where does that occur? Well, it occurs on hydrous oxides of iron, aluminum, and manganese, although around here iron is our primary player. It's what gives our soils the orange or red or gold colors, especially in our subsoil, we're aware of that. It's also occurs on humus, and it occurs on the edges of aluminosilicates. Going back to our clay mineral, this is the top of our clay mineral, this is the bottom, these are our planar surfaces, but there are also broken edges. And on the broken edges of clay minerals, you can get the pH-dependent charge. At the same time, you have permanent charge on your planar surfaces. Okay? So clay minerals can have both kinds of charge. So how do we get pH-dependent charge? Well, remember, it's due to the protonation or deprotonation of surfaces, the gain or the loss of hydrogen ions. So in a highly acidic soil, we've got a lot of hydrogen ions in the soil solution. And so a fair number of them tend to associate with the surfaces. So this is a broken edge of an iron oxide, and hydrogen has associated with those surfaces, such that in a highly acidic environment, let's say down about 4 or 5, this hydrous oxide actually has a positive charge. All right? Now let's say you lime that soil, and you raise the pH, and you reduce the hydrogen ion in the soil solution. What's going to happen? Well, some of that hydrogen is going to dissociate. So instead of having 2 hydrogens at every broken edge where there's an oxygen, there'll only be 1. So what's the charge now? Well, it's 0. It goes through a phase where it has no charge. Well, the lime's still reacting, hasn't gone to 6,5 yet, okay? So now, because there's a low concentration of hydrogen in the soil solution, both hydrogen ions have dissociated, and now we actually have the negative charge exhibited at every one of those exposed oxygens at the edge, the broken edge of the mineral. So iron oxides, depending upon the pH of the soil system, can be positively charged, uncharged, or negatively charged. And as we lime our agricultural soils, and then they go back down, because I'll show you this afternoon in a graph, the lime story is a roller coaster. The charge on these changes, all right? The charge they have this year won't be the charge they have in 2 years in all likelihood if we're doing anything to that soil. How does it happen on a humus molecule? Well, Melissa showed you one example of a humus molecule. This is another one. I like this. It shows you some of your basic units. Humus has a lot of these aromatic groups in it, all right? But it also has functional groups, okay? Carboxylic acid, hydroxyl, some of these other things whose names I don't remember anymore, peptides, okay? Well, it turns out that depending upon the pH this molecule finds itself in, these hydrogens on these groups can dissociate out into the soil solution. And as they do, charge develops at each of those functional groups. Okay? So pH-dependent charge is all about, is the hydrogen there? Is the hydrogen not there? All right? Turns out this is a area where a lot of people spend a lot of time looking at it. It turns out that there's a different dissociation pH for every group. So hydroxyls lose their hydrogen at a different pH than carboxylic acids. And to make it even more interesting for people like us, a hydroxyl near another hydroxyl loses its hydrogen at a different pH. So this is a nightmare, okay? But who cares? You just know that this is how it happens. It happens because as you go through a pH range, various ones of these either will or won't have a hydrogen ion associated with them. And when they don't, there's a negative charge originating on that humus. Now the interesting thing about humus, and this is just a tiny, tiny piece, a real humus molecule is probably 10,000 times this, okay? This is just a little chunk. The organic matter not only has surfaces like this, where they hold ions, but these surfaces in here actually are hydrophilic. So organic molecules can be absorbed onto those part of the humus molecule. At the same point, you've got ions absorbed at the functional groups. Okay? Humus is multifunctional in terms of its ability to absorb things. It can absorb things that are nonpolar, lipophilic, fat-loving. At the same point, they have charged surfaces that absorb cations. So in weed science, I'm sure, yeah, of course, you guys studied that a lot. Okay, so let's look at the cation exchange of some common soil materials. Look at 2 more graphs, I'm going to eat lunch. And this is pure materials. So if I had 100 grams of humus or 100 grams of montmorillonite, this is separated pure materials, all right? The cation exchange capacity of humus is huge, okay? Again, it depends upon what book you read, but one that I've looked at recently put it at 100 to 550. Vermiculite, it's the most power-packed of the clay minerals, 120 to 150. We do have some of that in soils here in Maryland. Montmorillonite, 80 to 120. Illite, 15 to 40, we got a lot of that in Maryland. Kaolinite, a lot of that in Maryland, 3 to 15. And iron oxides, 0 to 2, only if they're up near neutrality. If they're below that, they may have no charge, or they may actually have positive charge. So if you look at the pure materials, there's a huge difference in the organic colloid humus compared to the inorganics. And there's a wide range of differences depending upon the amount of isomorphic substitution in the clay minerals, and that's largely a function of how old that clay mineral is and what it started from. So let's look at soils, because we know that soils aren't just 100% clay or 100% humus. They have humus, they have clay, they have sand, they have silt, they have different kinds of clays, right? So things that have a sand textural class, they're down in that left corner of the textural triangle, tend to have CECs between 1 and 5 milli equivalents per 100 grams. Fine sandy loams are higher, loams and silt loams, clay loams, 15 to 30, clays greater than 30. Clay textural classes, soils tend to be very, very difficult to manage. We have some up in Carroll County. There's a very narrow range where they're tillable. They're either too wet or too dry. They take phenomenal amounts of energy to till. Their resistance is very high. So I know there's a common belief among some growers, usually more hobby growers, that, oh, the more clay I have, the better the soil is. Only up to a point, okay? Then it's not good anymore. Let's think about what factors affect the cation exchange capacity of a soil. How much clay do you have? How much clay-sized stuff? If you get a textural class analysis done on your soil, that'll give you at least a range within which your clay-sized particles are measured. But the kind of clay, whether it's kaolinite, whether it's illite, whether it's montmorillonite, the amount of humus, okay? Because it's the humified organic matter that has all those functional groups on that dissociate and cause charge, and also the pH, because we know that the hydrous oxides and the organic matter and the edges of the clays charge is dependent upon the pH of the system. So you might ask yourself, well, just how much of a difference does it make? This is from a classic study done out in California by Pratt, one of the big soil chemists out there back in the 60s. And they looked at 5 different California soils, and they measured the cation exchange at a whole bunch of pHs from 3 up to 8. Right? And you can see that in some cases, the difference in cation exchange as a function of pH was not particularly spectacular, although it was always a little bit higher at a higher pH. But in some cases, like these higher 3 soils, the difference is really astronomical. In this case, the CEC went from about 11 up to about 25. Looks like it's 18 up to about maybe 32. And here's one that's about 24 up to 40. So the difference in pH can have a huge impact, or it could just have a minor impact. All goes back to how much clay did you have, how much clay edge surface was exposed, how much humus, how much hydrous oxide. So there's always some change, and there can be really massive changes. Now, base saturation is something that you need to be aware of. It's on your list of knowledge areas. It's also used as an important parameter by some soil test labs. So base saturation, in essence, is the percentage of the exchange sites, the exchange capacity, occupied by basic cations. And the basic cations are calcium, magnesium, potassium, and sodium. Hydrogen and aluminum are considered to be acidic cations. And the rule of thumb is the greater the base saturation, the more fertile your soil is. So here's an example. If you sent a sample in to a soil test lab, and it gave you the following information: exchangeable cations were extracted and measured. They measured them in centimoles per 100 grams of soil. Okay, you have 3 centimoles of hydrogen, 12 centimoles of calcium, 5 centimoles of magnesium, 1 centimole of sodium, and 4 centimoles of potassium. What is the CEC of this soil? So what is the CEC of this soil? Well, it's nothing more than the sum of the exchangeable cations expressed as centimoles per 100 grams. If the lab already reported it in this measure, then all you really need to do is add these up. Right? So it's 3 plus 12 plus 5 plus 1 plus 4. Can you figure out the base saturation from this? Sure. You look at the basic cations, the calcium, the magnesium, and the sodium, divided by all the exchangeable cations, and you will, in fact, have the base saturation. So what is the CEC of this soil? Okay, very good. It's 25. It's 3 plus 12 plus 5 plus 1 plus 25. And what's the base saturation? Well, it's the 12 calcium, the 5 magnesium, the 1 sodium, the 4 potassium divided by 25, or 22 divided by 25, or 88%. 88% is a high base saturation. So the CEC is nothing more than the sum of the exchangeable cations expressed as centimoles per 100 grams. And since they were already reported on that basis, all you need to do is add them up. Sometimes you get your data on the basis of another amount of soil, and then you have to express them on the basis of 100 grams. So we distinguish between 2 kinds of acidity in soil, the active acidity and the reserve acidity. Active acidity is the hydrogen ion in the soil solution. That's the environment that the microbes and the plants are bathed in. That's their home, all right? But the fact is, we know that there's also hydrogen ion, there's also aluminum ion, there's other acidic cations on the exchange sites. That's called the reserve acidity. And I think we know by now that there's an equilibrium between the 2, right? So the active acidity, think of that as coffee urine example. The active acidity is the stuff you see in that little transparent arm that tells you how much coffee is in the urn, all right? Whereas the reserve acidity is what's in the coffee pot. And we know that what's in the coffee pot replenishes what's in the serving arm, right? So when we lime a soil, we are impacting what's in the soil solution. But in fact, if that's all we do, it's going to get recharged almost up to the same point, right? So we need to take into account both when we need to adjust the pH because it's not optimal for the crop we want to grow. Yes, we impact it directly through the active acidity, but we have to take into account the reserve acidity. Now, as this diagram shows, not all soils have the same reserve acidity. This one and this one have the same active acidity, but if you were to lime this soil with the same amount of lime you had on this soil, you would overlime it. And I'm going to tell you in a few minutes of all the reasons why overliming is not a great idea. So you might ask yourself, where does all this acidity come from? Why do we always have acid soils in this part of the country? Well, there's lots and lots and lots of sources of acidity. One is the nitrification or the oxidation of ammonium. Nitrification is just an oxidation reaction, as Dr. Tor will tell you a little bit later today. And most of our fertilizers and all organic sources contain ammonium. So if there's ammonium there, it's going to oxidize in a near-surface environment that's above a pH of 5.5 if the weather's warm enough for the microbes to work. And they're going to make 2 units of hydrogen for every 1 unit of ammonium that's produced, that's released into the environment, either from your fertilizer as it dissolves or the organic matter as it mineralizes. There's a 2-to-1 relationship. In addition to that, a lot of plant roots and microbes exude acids. They're usually small molecular weight organic acids, but they're acids. And we got a lot of folks living in the soil doing this, right? Rainfall is always slightly acidic, even if all it did was fall through the atmosphere and dissolve a little bit of carbon dioxide into carbonic acid. But around here, we have a lot of cars, and we have a lot of NOxes, nitrogen oxides in the air. And when rain falls through that, it picks up, it basically forms a nitric acid, right? And then if we've got any coal-fired electric generating plants upgrade, we don't have many of those anymore, there can actually be sulfuric acid in your rain. Now this was a huge problem back in the 70s and early 80s, much less of a problem now as electric generating plants have cleaned up. We have a significant problem with this simply because we have so many automobiles in this region. Then there's aluminum. Aluminum is an essential component of those aluminosilicates, those clay minerals, and many other minerals in the soil. And as those minerals weather and they release hydrogen or aluminum ion into the soil solution, aluminum has the potential to hydrolyze up to 3 units of hydrogen for every 1 aluminum that's released during weathering. And weathering's happening to some extent all the time. And then there's this oxidation of sulfur, and this is what happens in the acid sulfate soils. Sulfur is present as a sulfur dioxide, or elemental sulfur is the same thing, and as that's oxidized, there's 2 units of hydrogen released for every 1 unit of sulfur, either in your sulfide or in pure elemental sulfur. So you can see why there's acidification occurring. Now, the soils out west that aren't acidic because there's something in that soil to neutralize it. In the case of the soil that we had in the Rio Grande Valley, it had 8% calcium carbonate. It's going to neutralize acidity from now until the cows come home, right? But not back here. We don't have anything in our soils to neutralize the acidity. Thus, our soils tend to get acidic, and we are periodically counteracting that by adding a liming material. So this is a diagram similar to what you'll find in the Mid-Atlantic Handbook. You'll see various versions of this in various publications. And basically it's showing you the availability, not the presence, but the availability of certain nutrients at certain pHs. So we're going from 4.5 up through 8, all right? And let's just take the example of phosphate, okay? It's most available in the 6, 6.5 range. It gets tied up high and it gets tied up low. All right? We're not saying the phosphorus isn't there. We're simply saying it's not available. In the case of iron, look what's happening with iron. It's highly available in an acidic pH, and it becomes less available as the pH goes up. Right? This is one reason why you don't want to overlime your soil. In the case of calcium, there's a lot out here, above 7.5, and it really tails off. In the case of calcium and in the case of the magnesium, the calcium and magnesium have been leached away. They're not there anymore. In the case of phosphorus, it's just tied up. So this whole thing is talking about availability, but it's not telling you whether they're not there or whether they're bound so tightly they're not available. So it oversimplifies it from that point of view. That's one thing I don't like about it. But it has so many other good features we still use it. Okay? So notice that iron and manganese and zinc, they all become more soluble, and that's more available in low pH soils. To the extent that in some low pH soils, if you don't lime, you can actually run into problems with manganese toxicity. So much dissolves out of the minerals at low pHs that your plants aren't happy. Right? But if you raise the pH too much, you have inadequate amounts of that. And this is the one, induced micronutrient deficiencies are the #1 reason why you do not want to overlime. You want to lime based on a soil test, right? When you need it. Not just, oh, I haven't limed in 3 years, or oh, Uncle Joe limed, Well, Uncle Joe might have an entirely different kind of soil, right? He may be farming a silt loam and you're farming a sandy loam, all right? So don't get a soil test and follow it. Okay, so you can have micronutrient toxicities, you can have micronutrient deficiencies if you raise the pH too much. Aluminum's up here. Aluminum is not a nutrient. It's not a nutrient for plants, it's not a nutrient for us. As a matter of fact, it's a problem for plants and it's a problem for us, all right? You notice how there's no soluble aluminum above a certain point, and then it just takes off like crazy, all right? This can cause all kinds of problems with plants because aluminum tends to cause something called clubbing in roots. And that basically means they stop growing. They just curl up at the bottom and go, sorry, not a good place to live. So your roots don't explore the soil as they should, and they're left with a much smaller volume of soil to get water and nutrients. So aluminum's a bad guy. So we lime to reduce acidity, and it's helpful for all these reasons. It supplies calcium and magnesium, which in a highly acidic soil have leached away, if in fact they were ever there. It increases the availability of phosphorus and molybdenum. Remember, low pH soils have positive charge on those hydrous oxides. They can actually bind with phosphate and molybdenum and fix it. So the difference here, it improves their supply, but it actually adds calcium and magnesium because it's no longer there, whereas it makes the phosphorus and molybdenum that is there more available. It preconditions the soil environment for beneficial microbes that fix nitrogen. Most of the nitrogen-fixing bacteria don't like it if it's below pH 5.5. So if you want to grow soybeans or you want to grow alfalfa, and you're relying upon the nitrogen-fixing bacteria to supply the nitrogen to that crop, you've got to provide an environment that they find helpful. Lime, right? Liming also reduces the availability of manganese, zinc, copper, and iron, any of which can become toxic in highly acidic soils. And liming eliminates soluble aluminum. And you'd like to do that because soluble aluminum causes clubbing of roots and reduces the crop's ability to explore the soil for water and nutrients. Now, crops have a definite pH preference, although most of the ranges are quite wide. This is just a very, very small list. There are many lists and many publications. There's one book I have that must be 6 pages long on different crops, including all kinds of horticultural stuff. I don't even know what some of them are. But this is just some of the main crops grown here in Maryland. You can see that corn has a rather wide range. It can grow up to low 7s, so high 5 to low 7s. Wheat's about the same. Potatoes, 5.5 and below. Tobacco, less than 6. Soybeans, a little more particular here. You're trying to cater to your nitrogen-fixing bacteria. They don't like it if it gets too acidic. Alfalfa, a different strain of nitrogen-fixing bacteria lives in association with alfalfa. They're both nitrogen fixers, but they're not the same species, and it happens to prefer a higher pH. So if you're wanting to go into alfalfa, the advice is to get your soil in good condition and lime to a pH of 7 before you start. Now, this one on potatoes is very interesting. Potatoes themselves can tolerate a wider pH range, but they have a disease called scab that's caused by an organism called Streptomyces scates. Okay, and it turns out that it's an actinomycete, which, you know, depending upon what book you read, is a bacteria. It's not a bacteria. Boy, have they bounced that one back and forth. Anyway, physiologically, it's similar to a bacteria in the sense that below a pH of 5.5, it doesn't prosper. So you can have those organisms in your soil, but if you keep the pH below 5.5, it doesn't cause scab. Whereas if it goes above, it causes scab. Now, scab is no problem for us, you know, who cares, you know, but it downgrades the quality of the potatoes, so most growers can't even sell them. So in this case, we're maintaining the pH we are to control a plant disease, so we get a high quality crop, even though the crop itself, if we're in an environment where the pathogen didn't exist in, could tolerate a higher pH. So there's some little funky things like that to go on sometimes too. So anyway, we have target pHs for the crops in Maryland, and these were established many, many years ago. We recommend a 7 if you're establishing alfalfa, a 5.6 for tobacco, 5.2 for both Irish and sweet potatoes, 6.5 for most of the agricultural and most of the agronomic and most of the horticultural crops. Little subtle differences in some of the fruit crops, but they all tend to be up in the low 60s. How do we adjust soil pH? Well, around here, people usually want to raise it from where it is, so we use lime materials. And lime basically neutralizes acidity. It reacts with the hydrogen ion, and it raises the pH by taking the hydrogen ion basically out of play. There are times when people want to lower the pH. I probably get 1 or 2 calls a year about that. There are materials that can be used to produce acidity and decrease the pH. So the aluminum I talked about, remember aluminum hydrolyzes and produces 3 hydrogens for every aluminum. Well, if you want to increase the acidity of your soil, you can add aluminum sulfate, and that aluminum will dissolve, it will hydrolyze, and it will produce acidity. Iron sulfate is the same thing. They're relatively soluble salts. They dissolve, they hydrolyze, and they produce acidity. I always ask the question, what do you want to do that for? Especially for agronomic crops. Why would you want to reduce? Just be patient. In a couple years, it'll go down. But sometimes they want to do it. Elemental sulfur will work also. Elemental sulfur undergoes a similar oxidation reaction. However, that needs to be microbially acted upon. So these two dissolve. They're not they're not soluble as salt, but they're pretty soluble. Whereas this actually is insoluble, and in order to get the hydrogen ion produced, sulfur oxidizing bacteria have to colonize it and oxidize it. So that takes time. This probably takes a period of months. This probably occurs within a couple weeks. Stuff just has to dissolve, mix, diffuse. Okay. So is lime required? Well, it depends. You have to know what you're growing, and you have to know what the optimal pH range is for that crop. And if your pH is less than that, well, then you should consider liming. And if it's okay, you don't. Now, lime is viewed as being an expensive material. And I think part of that is you need a lot of it. You buy it in tons instead of hundreds of pounds. There is, shipping involved. So a lot of times when I talk to farmers about why are you putting all this nitrogen on when your pH is 5.2, they go, well, lime is expensive. See, agronomists think you should lime first and do the other things later. You should get your soil in good condition and then invest in the fertilizer. But that's not necessarily the way all of our clients out there in the universe think about it. Anyway, crops, as we saw, have different pH ranges, and if you want to, let's say you're taking land that's been, you bought an old farm, no one's done anything with it in a while, all right? And you want to put it in production and get some decent returns on your money soon. Well, you're going to want to look at the pH that it is now, look at the optimal pH range, and if you're very far off, I'd suggest investing in some lime, And it depends upon where you are now. If you're down at 5.2 and you want to grow alfalfa, yeah, you better do something. All right, because you're not going to get very good alfalfa growth at 5.2 because your rhizobia aren't going to fix the nitrogen. So it all depends. Now, how much lime is required? Well, that depends too, of course, right? You can have a pH of 5.2 in one field and a pH of 5.2 across the county in another property you're farming. One can be a sandy loam, one can be a silt loam. You need, even though you might have the same pH in the soil solution and you're going to grow the same crop, you don't have the same reserve acidity. All right? And that's why the lime requirement might be different from one field to the other. So you have to take into account the target pH of the crop. We just talked about some of them. The pH of your soil solution, and that's what you usually see on your soil test form where it says pH or pH water, and then your reserve acidity. Now, that may or may not be directly stated on your soil test report, but they should give you some indication of how much lime is required. Some soil test reports have pH and pH buffer. Anybody seen those? Okay. The buffer is another test that was done to estimate the reserve acidity. Unless you have an interpretive equation or a table, you don't know what to do with it, but they used it to calculate your lime requirement. So lime requirements can be done in 2 ways. They can be a chemical test, that's what the pH buffer is. It's a chemical test to determine how much lime is required. Or you can use some kind of decision support tool to estimate how much lime is needed. And the lime requirement is usually given in terms of pure, fine limestone. So if you're using something else, you're using domino sugar, you might have to adjust your rate. Right? Okay, the process we've used for years and hasn't changed is to look at the pH of the soil solution, the target pH of the crop, and the reserve acidity is estimated by this, by what I call a decision support tool that takes into account soil texture, which it gives you at least a range of clay contents, and physiographic province, which gives you some information as to what kind of clay you've got. So this is kind of an old procedure that Maryland never grew out of. Most states had this way of estimating reserve acidity until about 30 years ago when they started looking at chemical tests. We still use this. So let's look at how these soil buffer things might work. So first, the lab probably does the soil pH in distilled water, all right? And maybe they're able to use that same sample, or maybe they have to use a separate one. But anyway, they mix the soil with a carefully designed solution. These buffer solutions, I don't even know how people came up with them. It amazes me. Anyway, they're usually cocktails of stuff, all right? And depending upon which one's being used, some of them you equilibrate that mix for 15 minutes. Sometimes it's 30 minutes, but that's pretty short. That's not bad, all right? And then they measure the pH in the soil buffer mixture. And essentially, the buffer, depending upon which one you're using, is made at a certain level. And to the extent your soil reduces the pH of the buffer, they have equations that allow you to determine how much lime you should apply. And that's why there's either a lookup table or an equation that allows you to get from the pH in the buffer to the lime requirement. Well, one thing I want us to understand is that the same amount of lime on different soils might have a radically different effect. All right, and this is a very nice table. I don't remember where I got it anymore, unfortunately. But anyway, if you were to start out in all of these cases for these soils and they were at a pH of 4.5, you know, what does it take to increase them? Okay. Well, here we see that with a sand, which has a CEC of about 5, and that's high for a sand. All right. We can see that we can raise it from 4.5 up to 7 with a little over a ton of lime. Okay? Just go over here. Ton of lime. 4.5 to 7. All right? Whereas if you've got a sandy loam CEC at 10, and you for some reason wanted to go up to 7, it would take you over 2 tons. If you were a silty loam CEC of 15, you're at 4 tons. Right? 25 sandy loam, you're not even at 70s. Or to look at this another way, a ton of lime on a sand increases the pH up to 7. A ton of lime on a sandy loam only increases it to 6. You can look at this either of 2 ways. But please, always lime based on a soil test, and not just because it's time to do it. Okay, now, this is the roller coaster we're on in this climate. Remember, we've got rainfall. It's going to leach the bases away. It's going to leach everything away. There's always more hydrogen being produced. And so over time, even though we might add lime down at the, where are we here? 4.8 maybe. Pretty low, new land, hadn't been farmed in a long time. We add some lime. Okay, it increases the pH. So by the next year, we're up in the low 7s. Well, then we don't lime for a while. What happens? Well, it's going to go down. It's going to go down because the acidity is constantly being produced and the bases are being taken up by the crop or leached. All right? So it's going to drop down again. You know? So after a couple years, you might need to lime again. All right? Like going down to 5.5, 3 years, 2 to 3 years, that's not uncommon for a liming frequency around here, right? Well, it wouldn't if they were doing what they should. Okay, but by year 4, you can see that you're back down in a dip again. Okay, this is below the optimal pH. Let's lime again, so it goes up, and then in time it goes down. This is the lime roller coaster, the pH roller coaster we're on here with lime. All right? Constant production of acid-forming factors and leaching and crop uptake at the bases means that even though we may have the situation optimized this year, don't assume it's still optimum in 3 years. By the way, in Maryland, we're required for farms that come under the animal unit or money threshold to get soil test every 3 years. So you can see that in this case, a 3-year frequency of soil testing would kind of tell you where you are too. So when should lime be applied? Well, a lot of the old books basically said, you know, you need to apply the lime the autumn before. Right? And this is before we had a lot of double cropping too. The thought was, this was in the era where there was a lot of fall tillage anyway, because we believed in clean fields before Thanksgiving, all right? So you put your lime on in the fall and you let it react, and that's good because the lime comes in a variety of particle sizes and it takes time. But Mark Alley down in Virginia Tech did some work before he retired. I think he's retired now. And he looked at the efficacy of lime on alfalfa. Now, alfalfa is a pretty pH-dependent crop. You know, I mean, you make your rhizobia happier, you're not getting your nitrogen fixation done. And he looked at whether or not it was efficacious to apply lime at planting. Let's say you couldn't put it out in the fall before, you didn't have the money, it was too wet, whatever the reason was, you didn't think about it, you didn't have your soil test yet, whatever reason. So he actually put it on at planting. And we're looking at 3 rates here, 0, 1, 3, and 6. And this is alfalfa the year of planting. So you don't get a whole lot your first year anyway. It's not your big year. But you can see that even adding it at planting had a positive impact. So even though a lot of the old recommendations say add it ahead of time, add it the fall before, give it time to react, it's better to apply it at planting than to not apply it at all, especially for a crop like alfalfa that's so dependent upon an optimal pH for the rest of what you want, i.e. nitrogen fixation. Okay, so let's look at this. Cation exchange is affected by amount of clay, type of clay, amount of humus, pH, or all of the above. All right, all of the above. How much clay do you have? What kind of clay is it? How much humus do you have? And what's your pH? All of those impact how much cation exchange capacity you have. Good. You're going to nail that one. Okay. Any questions on this unit?